Welcome back to Learn Piezo. Today we'll be discussing the most simple circuit to drive a piezoelectric device at a frequency. And this frequency will be one where firstly we can control the frequency. So we're going to have an external frequency source. For the purposes of this video, I'll be using a function generator. However, in another video I showed how to use an Arduino for generating the frequency. And secondly, we're going to be using a DC power supply. So we are actually going to be using this control signal to access a higher DC voltage power supply. It's going to be 20 volts in order to apply that 20 volts to a piezo at the frequency of choice. This video is sponsored by my company Ultrasonic Advisors, where I provide product development support for companies developing ultrasonic transducers, circuits, and systems. So if you need product development support, contact me through the link in the video description for a consultation call to see if my services are right for you. So continuing with the circuit, we have as I mentioned, there's going to be a power supply, and for the majority of this video, when we get to the experimental part, we're going to be talking about a 20 volt power supply. We then have a simple component, and the key word here, as I mentioned, is I'm keeping things very simple. There could be many optimizations performed with the circuits described here, but we're going to keep things simple. And in that interest, we'll also end up with a very inefficient, but actually pretty effective circuit at the same time. So if you've watched some of my other videos, you'll know what will happen is the piezo in this case will respond like an RC time constant, and it will get charged with 20 volts. However, that's not really something that we're looking for. We want to apply frequency. We'll, treat the piezo like a buzzer, and then we'll generate a tone. Or if you have an ultrasonic transducer, you'd like to adjust that frequency to hit the resonant frequency of that ultrasonic transducer. So in order to accomplish, the charge and discharge of the piezo, we have to discharge the piezo. So this circuit charges the piezo very effectively, so we'll have to discharge the piezo by putting a switch here. And when the switch is closed, the current or the charge which is accumulated on the piezo will then have a means and method of dissipating. But this will also cause current to flow from the voltage source to ground as well, and that's one of the reasons why we have this resistor here, is to limit that current flow. So it is the main parameter here in the circuit. The only thing that's tunable is that resistor, and we'll be seeing its effect in the experiment and also in the theory that we'll describe here now. So in our circuit, we have two states. We have a state where the switch is open, and we have a state where the switch is closed. So we'll designate these. So in this case, the switch is open, this is closed, open, closed, open, closed. So we're essentially driving it with a square wave. So the voltage source will always be the same. So what we're going to designate right here, we're going to be counting this voltage right here, and we're calling it voltage, I'll say P. So we're going to be plotting voltage P here. So when the circuit is open, the piezo gets charged. So we'll have a positive voltage, and this will be 20 volts. And then when you close this circuit, when you close that switch, you will have 0 volts, because these potentials on these two sides of the piezo will be shorted. You're basically grounding that terminal of the piezo. So you'll have 0 volts at the closed state, and you'll continue to impose this 20 volts, but at the frequency of choice. And for this switch, we are going to use a MOSFET, which I'll describe in more detail in the experimental portion, but it's basically a voltage controlled switch. Or field effect transistor. So let's continue and describe with numbers what's happening. So we have two states. The first state is the charge state. And in the charge state, it's also the open state. And in the open state, we have a charge up according to the RC time constant. So let's say the voltage started at 0, and we now have an RC time constant determining how fast that voltage can achieve. Looking at how fast that voltage can achieve the proper value of 20 volts. So we have a resistor. So let's call that resistor because we'll be working with these exact numbers in the experiment. We'll have 100 ohms as a resistor, and we'll say the capacitance is 10 nanofarads. So in this case, we will have 1,000 nanoseconds as being the time constant, or that is also one microsecond. And if we want, and if we actually have that exact time, we'll have the voltage reaching, 73%, or forget whatever the time constant tells you. You'll reach that percentage of the final voltage. But in order to actually start to become similar to a square wave, let's say we need 5 time constants of speed minimum, and that would be then depending on which frequency we use. So if we translate this 1 microsecond, it actually becomes 100 kilohertz. It becomes 1 megahertz. And in order to assume, let's say, that the response will then equal a square wave, we need to be even faster than that. So let's say we need to be 5x faster in order to have decent performance. So we would say our frequency signal is going to be limited to 200 kilohertz theoretically from this charge sequence. Then from the discharge point of view, what's governing how fast this device will discharge? Well, once you have shorted this, there's no resistance, so we have a capacitance, but the resistance equals 0. Therefore, the time constant is about 0 too. So it essentially has no limitations on your performance. But that being said, we have now our this path when the circuit is closed and discharging. We have this path also active, which is a direct connection between our voltage source and ground. So we are going to be running current there for sure. So we mentioned we have 20 volts and 100 ohms. So 20 volts, 100 ohms, that's 200 milliamps of current. And if we then look to calculate power, equals I squared R, we would then surmount to a power of 0.04 amps squared. So I multiplied this number squared, multiplied by 100 ohms. So we go 1, 2, so we have 4 watts. However, we have a duty cycle of 50%, so we end up with 2 watts of energy. So if we actually wanted to drive this at, let's say at 1 megahertz itself, like I said, we can't drive at 1 megahertz because we won't reach the full voltage. Let's say we needed a 5 megahertz signal in order to, 5 megahertz capability of one time constant in order to drive at 1 megahertz. Then we would need to reduce this 100 ohms by 5 times. So we would need to make that 20 ohms. And when we make this 20 ohms, so 20 ohms, 20 volts, we would have 1 amp during this discharge portion running through our resistor to ground. So if we do this I squared R again, we actually end up with 20 watts, which is not something a normal resistor will handle. Thankfully I'm going to be using a 3 watt resistor, which is quite chunky, as you'll see. But we'll be working under its maximum limit. We'll be working around 2 watts, not the 3. So let's go ahead and talk about our experiment to show this. So we have our piezo buzzer, or pickup element. So we have our piezo element, and we have soldered leads to it. And I've measured its capacitance at 3 values. So at 100 hertz, at 1 kilohertz, and at 10 kilohertz. So we have 16, 15, and 11.7. So it seems like this number is not stable, apparently, the capacitance measurement. I also highly recommend this LCR meter for making standard measurements on your piezoelectric devices. And let me know if you have any further questions on that. So I'm basically testing the piezo element here. So we need to provide a frequency response, and this is a custom program that I have, which measures the frequency response of impedance and frequency here. And we have several resonant frequencies. So we have one resonant frequency at 5 kilohertz. We have another at about 8 kilohertz. Another here about 13, and another here about 34 kilohertz. And after every one of these resonances, the capacitance will drop. So we measured about 10, and there have been 2 significant resonances since then. So the capacitance, of course, is going to decrease as you keep increasing frequency. The reason why capacitance decreases as you cross resonant frequencies is that part of the mechanical response responsible for your capacitance, because there's the electromechanical contribution to capacitance, and there's also the intrinsic capacitance. Now, when you cross your resonant frequency, now that mechanical component, that specific response of the material is now diminished. Therefore, your capacitance will start to decrease as you are exceeding your resonant frequencies. So in order to get like kind of a general, capacitance value to use, because I'm assuming we're using RC, we're doing time constant stuff. So in order to do that, I ran a short circuit, open circuit calibration, which kind of gets you on the piezo, which tries to approximate the capacitance of your material. Of your circuit, test circuit. But if you actually have a device under test, you'll end up measuring an effective capacitance across the whole range, and that's what I use here. This is an effective capacitance. Done kind of inversely, so I didn't have to kind of go in and do that calculation. So now we're going to start describing the circuit. And the heart of the circuit is going to be the switch, which is our MOSFET. And these switches, a MOSFET can only conduct in one direction. So typically when we draw this sort of diagram for our switch and we connect it, current is free to flow either direction depending on how you apply your potential. But for the case of the MOSFET, it can only flow in one direction. So the voltage controlled switch, as you see here, is the gate, the drain, and the source. So the gate is actually, you apply your voltage here, you apply your square wave from your source here at the gate, which then opens and closes the connection in between the drain and the source, which opens and closes that connection. But for a MOSFET and the way the semiconductor devices are created and theoretically work, the current flow is only going to happen in one direction. Therefore, when we had our circuit way in the beginning, we have to orient our source here and our drain there. And our gate would be then applying our pulse train by which we control our cycle. This specific MOSFET can have up to 100 volts. The IRF 520. And in order to fully close the gate, fully close the switch, it recommends 10 volts. And now these values are sort of pulled off at certain points. We'll be applying 5 volts similar to a Arduino. So we'll be actually applying 5 volts. And the source, again, it's going to be hooked up to the ground, as was shown on the initial diagram, where the bottom of the switch was hooked to ground. So it forms a gate source voltage, because the gate voltage references the source, but the source is also the ground. So it's basically a gate ground voltage. Basically, it's just whatever the gate voltage is in this case. But it's not always, the source is not always put to ground, but we're, again, going for a simple circuit here. So we have how many volts? We have 20 volts, right? Between the drain and the source, between the two parts of the switch. We have 20 volts. So this is 1 volt. This right here is 10. This is 20. This line right here, that's 20. And we're putting 5 volts across. So we have the second up, so we have this point right there. So if you put 5 volts across, and you have 20 volts on your drain source, on your which is on your piezo and between piezo and ground, and you're trying to close that switch, what is the effective resistance of this switch? The effective resistance is essentially, you can think about it as V equals IR, or voltage over current equals the effective resistance, the DS in this case. So we have This is 1 amp. This is 2 amps. So we have 2 amps here and 20 volts. So it effectively forms it's going to form about a 10 ohm load, which is significantly less than the 100 ohm parallel resistor, but it will still present some heating in that. So in order to provide a more efficient device, you can choose a different MOSFET, which will be more efficient. This is actually what I had on hand right now, and you kind of see I had to dissect it from another circuit and attach some leads. But yeah, this is not the best device to use for this level of current flowing, but we're gonna roll with it and see what happens, and it works quite well still. So this is setting up the circuit here, and we're going to start with the switch. So there's 3 pins here. The first is the gate. And the second is a drain. And the third is a source. So these are the 2 which have the switch. And this is the control. So between the drain, we put a resistor, and this is a 100 ohm resistor. It's a 3 watt rated. That's why it's so large. A larger resistor, the better the watt rating. And between the resistor and the drain and the switch, we have the voltage. So here's our 20 volts being presented to that resistor. The piezo is actually also at the base of the resistor and also connected to the drain, that switch. So basically what we've done so far, we put our voltage source, we put our piezo, we put a switch, and we've also put our piezo right there. That's what we've done. That's what we've done so far as this circuit. Next, we connect the piezo and the switch here by putting the black or ground terminal. It's not really a ground terminal of a piezo, but the black wire, the other side of the piezo to the other side of the switch, which is the source, and this is the drain. And the gate is kind of separate from that. It's basically the control signal. We also put a resistor in between the gate and the source. And the reason we put that resistor there between the gate and the source is that when we have a charge, basically the gate is a capacitor, and when you charge that gate capacitance, you close the circuit. But that capacitance is, if for some reason, let's say you unhooked your cable or your whatever you're using to supply voltage to the gate, you unhooked it, that charge will still remain. So the resistor that we put there allows a pathway for the charge to dissipate. And when the charge dissipates, the transducer, the transistor will turn off by itself. But the resistor value should be high enough that it won't affect your performance. So in this case, I chose 10 kilo ohms. So it's quite large. It won't disturb the operation of the gate. However, it will turn off itself if left alone, even if it was charged. Here I have added the ground terminal. So where we're at right now, I just put the ground, basically from the voltage source, connected that, and there we have the circuit. And here's another image there. So using a function generator, we hooked up to the gate This should be 1 over, but basically, remember the MOSFET had 3 legs. The first one was the gate, so we connected the gate to the signal generator, and the ground of the signal generator to the ground of the rest of the circuit. Therefore, the gate signal is referenced. So now we've actually completed the circuit and are ready to plug in our power supply and supply that 20 volts. So we turn on the power supply. On power. DL. Okay, spelling today is not working the best for me. What can I say? So DC power. Voltage. So we have 20 volts. And the yellow, that's the supply voltage. And the blue is the piezo voltage. Basically the voltage after resistor. Piezo voltage. After resistor. And that is right there. So that's the piezo voltage, and we're obviously referencing to ground. So that delta voltage is the piezo voltage, which we're actually trying to stimulate. So we set the gate voltage to a 1 kilohertz square wave, and the offset is 0 volts, and the peak is 5 volts, as you can see here. And the duty cycle is 50%. So yes, we get a square wave, like we said, like we get when the circuit, when the gate voltage is low, meaning 0, the value is closed. We have a high voltage. Basically, the piezo charges up. But when we close the circuit, then yeah, we've shorted out the piezo terminals, and this then continues. And this is again this is the 1 kilohertz response. And if you zoom into this, we'll actually see additional harmonics. And this harmonic, as I put the cursors here, this other resonant frequency which is ringing, it actually ends up being, the period ends up being 7 microns, or 7 microseconds, which is, in our case, 143 kilohertz. And if we apply a square wave at 30 kilohertz, we'll receive this response where we have, that same harmonic repeating itself, but we are able to stimulate voltage. And these scales are out of place. The scale of the supply voltage and the piezo voltage, they're not the same, 5 volts and 10 volts, but the piezo voltage or the supply voltage is going to be right there with the peak voltages from the piezo voltage. So it's working well, although the harmonics, which is the result of using a square wave drive, but we have successfully delivered 30 kilohertz of a sine wave at 20 volts peak to peak. So using this simple circuit, and a couple of other things we can probe into. So increasing the frequency further, we then get less ringing. We get this time constant. Basically, it's going to be now more related to a resonant frequency response. because the higher the resonant frequency of your device, and technically the smaller it is too, the faster the potential it has to reach the maximum voltage, or to reach that supply voltage in charge. So mechanical behavior actually creates that charge. Mechanical behavior dictates the rate of increase in voltage. So I mentioned earlier we had that 20 volt load. This is 20 volts applied to our circuit. So this is the power supply. We have 20 volts applied. We had 100 ohms. And I said that resulted in 0.2 amps, or 200 milliamps. And because of because we're only on 50% of the time, we should get 100 milliamps. And this is actually what we get here. Now, as we increase our frequency, we do start to increase in this current. And that's actually because our MOSFET gate drive voltage from the function generator starts to dip down, because as you increase frequency, the charge needed, or the capacitance, requires that you supply more current, and there are specific circuits which are developed to supply as much current as the gate needs to be turned on, because in order to turn on the gate, you have to supply a certain amount of charge, which takes a certain amount of current, and there are special ICs called MOSFET drivers, which can better accomplish this. But at the basic level, like at 30 kilohertz or 1 kilohertz, you'll have this ideal characteristic. And I think I mentioned back here, I think I made a mistake here. It was seemingly odd to me. That we're going to be working at 2 amps. It was actually 200 milliamps. So although this is we do, and it's potentially possible to have 2 amps flowing, because you have 20 volts over the drain to source. But as soon as that starts to, that the charge starts to flow off the piezo, which it happens very quickly, as soon as that charge starts to flow off, the voltage will plummet quickly to 0, and on its way, the current will start to decrease. So you will not necessarily get this 10 ohm load the whole discharge cycle. You may get that kind of response at the very beginning, but that kind of drops off quite quickly. So we mentioned that we have, this current matches, which is nice to see. If we increase our frequency to 100 kilohertz, we see this behavior, where we're not quite able to get and charge our piezo, and this could be because of a couple of reasons. It's likely going to help if we decrease that 100 ohm resistor, let's say to 20 ohms. That's likely going to help. We are actually reaching the maximum voltage, so it's probably related to the frequency response. So part of it is going to have to probably do the resonant frequency, the mechanical response, because the piezo can only react as fast as its resonant frequency, period. That also affects, that ringing that we saw earlier, where it came up and it rang. That that initial curve upward is part of that charging process. Also, adding a capacitor, adding a storage capacitor at the voltage source, because the power supply, the instantaneous current that it can provide, there's some level of inductance in the output. So right now we have this case. We have our resistor, we have our crystal, and we have our switch, and all of this is grounded here. But if we put a storage capacitor between the positive and negative voltage, when the circuit needs more current instantaneously, it can release that from the storage capacitor. So that these couple of things can also help. But definitely for like something 40 kilohertz, this circuit will be very effective, especially if you use a resonant device. The capacitance will be very low for a resonant device, and it'll be mainly a resistive load. So that will also then affect the performance. So basically, depending on what you are driving, see, if you notice here, the whole circuit, or for now we're just talking about that resistor, it has a large dependence on what the capacitor is, or what the piezo you're driving is. So the driving circuit has to be optimized and intentionally made toward your test device and your test, toward your piezo. However, if you're using like a general purpose amplifier, that's not really a concern. But when you're going into a commercial device, you would need to consider your circuit and your test device, because if you suddenly change your topology of your system, you would need to change your circuit to better drive that. So I hope you enjoyed this video. Again, we covered the the simple circuit for driving a piezo. We covered different topics like charge, discharge. We looked at the resistor and understanding passive components with regards to the circuit performance metrics. We also looked at power dissipation in terms of that passive component. We also talked about MOSFETs. If that was new to you, I hope that discussion I provided was useful. Alright, thanks for watching, and look in the description for additional information.